Hello Math 1680 students. I'm making this video in response to a student who asked me a question about this exercise set. This exercise set is exceptionally difficult because it deals with real problems in real-world application. Not just realistic, but real problem. Okay, let's begin. The article, A Trial of Lopinavir/Ritonavir in Adults Hospitalized in Severe COVID-19, New England Journal of Medicine, published May 7, 2020 by B. Kao et al., reports the following. A total of 199 patients with laboratory-confirmed SARS-CoV-2 infection underwent randomization. Among them, 99 were assigned to the treatment group, and they actually received the real medicine. And the other 100 were assigned to the control group, the standard care group. Everything else is the same, but the medicine was placebo. The article summarizes its main results as follows. Mortality at 28 days was similar to Lopinavir/Ritonavir group and the standard care group, and those numbers were 19.2% versus 25.0%, with a difference of negative 5.8 percentage points. Okay, before starting this, let me make just a little bit of comment here. This medicine, Lopinavir/Ritonavir, is originally a HIV medicine, not designed for SARS-CoV. So no wonder the result was not very good. The researchers say the result was similar between the treatment group who actually received the medicine and the control group, the people who did not receive the medicine. And look at the sheer number. The mortality rates are extremely high, 19.2%, 25.0%. Nowadays, things are a lot better, so I don't want to scare you. It's not too bad. This study was conducted at, this article was published at May 7th, 2020. So the study must have been conducted about a month before that. So we are talking about late March, maybe up to early April. And at the time, doctors had really nothing. They knew nothing. They had to start somewhere, and certainly they did not have the antibody cocktail President Trump received. And they didn't have the steroid package, the steroid cocktail package either. And they didn't even have hydrochlorophyll and virtually nothing. And out of desperation call, people used HIV medicine. And this is the result. And not coincidentally, the mortality rates are extremely high. Okay, so much for the background, and let's do mathematics. We are doing two sample inference here, treatment group and control group, two independent groups. For that, what is the standard error formula? Remember the Pythagorean law? SC is equal to square root of first standard error squared plus second standard error squared. Does everybody recall this formula? Now, how do you get SC1 and SC2? These are all about proportions here. There's no measurement here. Do you see any other units like inches or centimeters or milligrams or things like those? No, you're looking at just proportions. So we have to use this formula. SC is equal to square root of P1, how do I remove this window? Over N. We have to use this formula, but then again, we have to do this for two groups. So SC1, we're going to need 1. For SC2, we'll have something similar. Let's put a little bit more space in between. P2, 1 minus P2 over N2. You have to remember these formulae. Okay, so this is a standard error for the sample study, and in order to find it, we need two standard error computation, one for the treatment group and one for the control group. This is the main idea behind the two-sample inference. In actual medical study, almost all the time you use two-sample inference. You need randomized treatment group and the control group. And this is the perfect setting. And if you do not have the controlled study, then the result is just unreliable. You just have anecdotal data, and that's not really helpful. And by the way, these high mortality rates are the 28-day mortality rates of the people who are already admitted to hospital with severe COVID-19 case already. And that's why mortality rates are that high. And if you just count the people who got infected, the mortality rate is much, much, much smaller, less than 1%. All right, now, how do we get this blue and red? Treatment group, control group. Okay, treatment. What are the people who received the medicine? Let's see, let's look at some numbers. First two lines are completely irrelevant as far as mathematics is concerned. Let's look at these numbers here, down here. 199 patients, that looks like a sample size, but where does it fit? Is it N1 or N2? Is it related to the people who received medicine or those who received placebo? Yes or no? Which is it? The answer is neither. It's neither N1 nor N2. Sometimes there are some confusing numbers, third numbers to confuse you, and this is one such situation. Now, let's go to the next number. 99 were assigned to the lopinavir-ritonavir group, so these people actually received medicine. Now, what is this? 99. What's this? Well, I'll give you a hint. These people actually received medicine, so I'm highlighting it in blue. How about this? 100 people, they belong to standard care group. They did not receive medicine. Actually, they received fake medicine, placebo. So these go to the control group. The color coding will help you. Mortality at 28 days. I don't think there will be anybody who will be confused with this 28. Is this an important number? I don't think there's anybody who would do this, so let's just move on. Now here are some important numbers. 19.2% mortality rate, 25.0% mortality rate, and then finally the difference of 5.8 percentage point. Which is which? 19.2%. What are these? Is this coming from the people who received medicine or not? The answer is yes, it came from the treatment group. And this comes from the control group. Okay, I'll stop here. This is what you have to find out. And in order to find this one out, you have to get SC1 squared plus SC2 squared. We need those two. Blue and red. And how do you get blue and red? You get blue from blue numbers, the treatment group. And you get red from the red numbers, the control group. The rest is left to the students. Let me go back again. Everybody should remember this formula. SC equals the square root of SC1 squared plus SC2 squared. Write it down in a formula sheet somewhere and prepare. This applies to all two-sample inferences. Okay? And in real-life application, most of studies are two-sample inferences because you want to control. You want to compare. You want to compare two effects, leaving all the others the same with sufficient randomization. So we use two-sample inferences all the time. But theoretically, it's harder because we have to consider two standard errors. How do you get your first standard error? Well, if this is measurement, then you're going to get sample standard deviation over square root of n. You're going to get that, but this is not a measurement. This is proportion. So unit formula for the proportion. P1 minus P over n. Square root of P1 minus P over n. And you have to use it for treatment group. Okay? So we have two competing proportions here. Which one is for treatment? Which one is for the people who receive the medicine? And then we have two competing sample sizes here. Which one corresponds to the people who received medicine? Okay, that's 199 total. That may confuse you. So be careful about that. But please note that this is nothing more than the sum of these two. So if you know these two, you're going to get this sum. So this doesn't really give you any new information. Same goes to this. If you know this blue and red, you can always subtract and get 5.8% of difference. 5.8% point of difference there. So this does not give you any new information. So that's something you'll have to screen out, at least for the time being. So in this kind of problem, you have to use the formula for two-sample inference, but even more importantly, you have to read through the problem and then find out what are critical numbers, what are important numbers that corresponds to which, and what are not so important numbers that you should discard, and what are important numbers that go to the other formula. It's not easy, but here we go. And as far as the computation is concerned, I'm not helping you. I'll stop here.